Okay, here we are on page 4 of discrete random variables, HL addendum, number 9. The score random variable x obtained by rolling a biased pentagonal die has the probability distribution as follows. So what do they mean by a biased pentagonal die? So it's kind of crooked or something. So as a result, the chance of getting each number is not the same. Normally you would expect each number in a pentagonal die to have a 1/5 chance of coming up. In this case, you have a different probability for each number, and none of them are 1/5 actually. So as usual, whenever they have a probability distribution and problem in the IB, they ask you to solve for A first, and what you use to figure out what A is that all the probabilities added together will give you 1, right? So looks like the common denominator here is 1/12. So let me express everything as a fraction in 1/12. So that'd be 2/12, 4/12, 1/12. A we don't know, and 1/6 is 2/12. So if we add up everything except for A, we'll have 2/12 plus 4/12 plus 1/12 plus 2/12. That would give us 9/12, which makes A 3/12, right? So A would be 3/12. Hence find the expected value of x and the variance of x. And 3/12 is 1/4. So we can see if we put 1/4 in for A that no, it's not symmetric or anything that would make it easy to figure out what the mean is. So we do need to use the calculator. Or we could figure out by multiplying together the probability times the x value, we could add them all together and find it, but let's use the calculator. So stat edit, we're going to put 1, 2, 3, 4, 5 here on the left side, 3, 4, 4, and 5. And on the probabilities, we're going to put 2/12, 2 divided by 12, 4 divided by 12, which is 1/3. We're going to put 1 divided by 12, and we're going to put 3 divided by 12, and we're going to put 2 divided by 12 again. And we're going to do stat calc, one of our stats, L1, L2, and the mean is 2.92. And the variance is sigma 1.38, and we're going to square it. Okay, so let's see. We could also take sigma squared and subtract 2.92 squared, but I think it's 1.38 squared is easier. So 1.38 squared, 1.90, so 1.9. Okay, and then now we're going to use the rules to find e of 2x and variance of 2x without going to the calculator and changing things. So if we have e of 2x, it's the same thing as 2e to the x. 2e to the x is 2 times 2.92, which is equal to 5.84. Okay. And the variance of 2x, you remember our rule, if we have the variance of ax plus b, we ignore the b, and it's equal to a squared times the variance of x. So basically, we're going to take the coefficient out and square it, and multiply that times the variance of x, okay? So the variance of 2x is equal to 2 squared times the variance of x. And the variance of x is equal to 1.90, so that would be 4 times 1.90. 1.9 times 4. Oops. 1.9 times 4. So that's 7.6. Okay? And last row. The expected value of x minus 1. So the expected value of x minus 1, what that does is it shifts the entire distribution to the left by 1. So that's equal to mu minus 1. So it's equal to e to the x minus 1, which is equal to 1.92. It's 2.92 minus 1. And the variance of x minus 1, remember when you shift the probability distribution to the left, it doesn't change the variance because the dispersion or the width of the distribution stays the same. So it's still equal to 1.90. Okay, so let's move on to 11. Use the properties of expected value of x to prove that e ax plus b equals a times e to the ex plus b. So first of all, we know that if we have e of a plus b, that's equal to e of a plus e of b. So we can break up that into eax plus eb, right? Then we know that e of b is just equal to b, because the expected value of a constant is just a constant. And we also know that if we have e of a coefficient times x, that we can factor the coefficient out, because multiplying every single random variable by a coefficient is the same thing as multiplying the coefficient times the expected value. So there we have it. Okay. B. So I did neglect to put the specific y distribution descriptions here, so I put them in. So we're going to do 1 and 3. And for 1, the description is y equals 3x plus 4. So if we know that the expected value of x is 3, then we can figure out the expected value of y, because the expected value of y would be 3 times the expected value of x plus 4. So that would be 3 times 3 plus 4, which is 9 plus 4, which is 13. For this next one, we have the y equals 4x minus 2/3. And in this case, I think the easiest thing to do is distribute the 1/3. So if you have that the random variable x is always going to be multiplied times 4, subtracted 2, and divided by 3, that's the same thing as multiplying it by 4/3 and subtracting 2/3. So and now we can approach it the same way as before. The expected value of y is equal to 4/3 times the expected value of x minus 2/3. So 4/3 times the expected value of x, which is 3, minus 2/3 is equal to 4 minus 2/3, which is equal to 3 1/3, which is equal to 10/3. So on number 13, suppose that y equals 2x plus 3, where x is a random variable. Find in terms of e to the x and e to the x squared. E to the y is equal to, this is an easy one, just like before, 2 e to the x plus 3. So that's it. They didn't give us e to the x, so we just leave it like that, right? E to the y squared, this is equal to the expected value of 2x plus 3 squared. So let's expand that. The expected value of 4x squared plus 12x plus 9. Now let's break it down. This is equal to the expected value of 4x squared plus the expected value of 12x plus the expected value of 9. The expected value of 9, of course, is 9. The expected value of 12x is 12 times the expected value of x. And the expected value of 4x squared is equal to 4 times the expected value of x squared. Okay? That's it for that one. So the variance of y, we're going to use the result from b to find the c. So the variance of y, if you remember, is equal to the expected value of y squared minus the expected value of y quantity squared. So we just found the expected value of y squared in the previous result. So all we need to do is find the expected value of y, which is from part A, and we square that. So let's see, we'll have 4e to the x squared plus 12e to the x. Oops. Plus 9. Then we subtract e to the y squared, which, if you remember, is this expression squared. So if I square that expression, I'm going to get this, minus 4e to the x squared plus 12e to the x plus 9. So the 9's are going to cancel out with each other, 9 minus 9. The 12e to the x is going to cancel out with this 12e to the x, 12e to the x minus 12e to the x. And then we're left with 4e to the x squared minus 4e to the x quantity squared. So like this is different because we're squaring the e to the x value. Okay, and that's it. 25F3 on page 804. Suppose that the random variable x has the binomial distribution with 3 trials and probability p. So the probability distribution looks like that. Find p of 0, p of 1, p of 2, and p of 3, and display your results in a table like the one opposite. So first let's do p of 0. So first we'll have the binomial coefficient, 3 chooses 0, which is just 1. Then we'll have p to the 0, which is 1. And then we'll have 1 minus p to the 3 minus 0, which is 1 minus p cubed. Then I'm going to write that here, 1 minus p cubed. Let's do it for x equals 0, for x equals 1. That would be the binomial coefficient 3 times p to the first times 1 minus p squared. So that would be 3 times p times 1 minus p squared. The next one would also be 3, but it would be p squared times 1 minus p. And the last one would be p cubed. Okay? All right, then we look at b. Use mu equals sigma pixi to show that mu equals 3p for this distribution. So what we're going to do is we're just going to multiply these two, multiply these two, multiply these two, multiply these two, and add everything up. So let's try that. So 0 times 1 minus p cubed gives us 0. 1 times 3p times 1 minus p squared gives us 3 times 1 minus p squared. And 2 times 3p squared times 1 minus p gives us 6p squared times 1 minus p. And then 3 times p cubed gives us 3p cubed. And then we add them all together. And we're going to get 3p times 1 minus 2p plus p squared plus 6p squared minus 6p cubed plus 3p cubed. And then we're going to multiply this one out. 3p minus 6p squared plus 3p cubed plus 6p squared minus 6p cubed plus 3p cubed. Then we're going to combine like terms. So p cubed, p cubed, p cubed. Looks like we have 3 minus 6 plus 3, they all cancel out. There's nothing left. Then we'll do, 6p squared minus 6p squared gives us 0. So that cancels out too. We're left with just 3p. Okay, and we were trying to show that mu equals 3p, and we just did. Now we're going to use this relationship to try that to show that sigma equals that expression with the square root. So first thing we're going to do is we're going to try to find the first part of sigma squared, which is this part here. We're going to square each one of the x's, and we're going to multiply it times the probability distribution. So the first one yields 0. The second one, again, yields 3p 1 minus p squared. And the third one yields 4 times 3, which is 12p squared times 1 minus p. And then the last one yields 9p cubed. So let's simplify that. So the first term is going to expand to 3p. Oops, do you see what I did? I wrote something wrong here. It's 1 minus p squared, not 1 minus p squared. So it's going to be 3p times 1 minus 2p plus p squared plus 12p squared minus 12p cubed plus 9p cubed. And then we're going to distribute the first one, 3p minus 6p squared plus 3p cubed plus 12p squared minus 12p cubed plus 9p cubed. Okay, so let's combine the p cubed. So 3p cubed plus 9p cubed minus 12p cubed. Oh, they all cancel out. Okay, what about 12p squared minus 6p squared? That's equal to 6p squared. So it would be 3p minus or plus 6p squared. And that is this part here. And then I subtract mu squared, which would be 3p quantity squared, which would be 9p squared. So that is equal to 3p minus 3p squared, which is, you can factor out the 3p, and then you end up with 3p 1 minus p. And that's sigma squared. And the sigma is equal to the square root of 3p times 1 minus p. Okay, because I'm taking the square root of sigma squared. All right, last thing. We're going to start talking about Poisson distribution now. And so French mathematician Siméon Denis Poisson discovered the Poisson random variable as a limit of the binomial distribution as the number of trials approaches infinity. That sounds fascinating, doesn't it? So that's the next page. By the way, there's only one E here.